In this paper, the author introduces a novel fermionic description of flagged k-theoretic symmetric polynomials, which can be seen as a k-theoretic counterpart of flagged skew-Schur polynomials. The author's proof relies on the Jacobi-Trudi type formula established by Matsumura. This result generalizes the author's previous works on fermionic descriptions of skew-Grothendieck polynomials and multi-Schur functions. The flagged skew-Grothendieck polynomial g lambda, micro, f per gram, x, is defined using the generating function, 3, and the determinant formula, 4. This polynomial is different from the one defined in 1, but coincides with it under certain conditions. The main theorem, Theorem 3.2, provides a fermionic description for the flagged Grothendieck polynomial, utilizing concepts from vertex algebras such as fermion-Fock spaces, vertex operators, and vacuum expectation values. The fermion-Fock space F is the left A module generated by the vacuum vector, 0, where A is the calgebra generated by free fermions psi n and psi asterisk operator n element of Z, with anti-commutation relations. The dual Fock space F asterisk operator is the right A module generated by the dual vacuum vector, 0, and there exists an anti-algebra involution on A that induces a linear involution omega. F right pointing arrow F asterisk operator. The vacuum expectation value is a unique CBI-linear map, 5, that evaluates the expectation value of a product of vertex operators applied to the vacuum vector. The paper emphasizes the fact that the fermionic descriptions, 13 and 19, are not found in the previous work on multi-Schur functions, suggesting there is still room for generalization of fermionic descriptions of k-theoretic polynomials. The work is partially supported by JSPSKAKENHI grant numbers 19K030655, 22K03239, and 23K03056. The research paper presents a comprehensive analysis of flagged k-theoretic symmetric polynomials, utilizing the concept of vertex operators and their commutation relations. It begins by defining the normal ordering of monomial expressions in terms of psi n and psi asterisk operator n, which is crucial for understanding the algebraic structure of the operators. The Hamiltonian operator h, x, and its dual h asterisk operator, x, are introduced, along with the vertex operators eh, x, and eh asterisk operator, x, which play a key role in the development of the flagged skew-Grothendieck polynomials. The paper then discusses the commutation relations between the vertex operators and fermion fields, providing equations, 79, that demonstrate how these operators interact with each other and with the fermion fields. These relations are essential for the calculation of the flagged skew-Grothendieck polynomials, as they allow for the manipulation of the operators and fields to obtain desired expressions. The main result of the paper is presented in equations, 11 and 12, where the flagged skew-Grothendieck polynomials g, f per gram, n, x, are expressed as a series of fermion fields and vertex operators. This result provides a novel way to compute the flagged skew-Grothendieck polynomials using the algebraic structure of the vertex operators and fermion fields. The paper concludes by noting the difference between two rings, C, Z, beta, and C, beta, Z, emphasizing the distinct properties of these rings in relation to the flagged skew-Grothendieck polynomials. The paper introduces a novel approach to describe flagged k-theoretic symmetric polynomials using fermionic expectation values. It begins by establishing a relationship between the flagged Grothendieck polynomial and its fermionic description, as expressed in equation 13. This relationship is crucial for the subsequent analysis. The main theorem of the paper, Theorem 3.2, provides a detailed expression for the flagged skew-Grothendieck polynomial g lambda, micro, f per gram, x, in terms of fermionic expectation values. This expression, given in equation 15, involves the use of two types of operators, a and b, which are defined in terms of their respective input variables, z and wj. These operators are then used to calculate the determinant of a matrix, as shown in equation 16, which represents the flagged skew-Grothendieck polynomial. The paper also delves into the properties of the a and b operators, providing explicit formulas for them in equations 11 and 12. These formulas reveal that the A and B operators can be expressed as sums over flagged Grothendieck polynomials, with coefficients involving powers of the variables z and wj. Furthermore, the paper demonstrates how these operators satisfy certain recursion relations, as indicated in equations 11 and 12, which further elucidate their structure and behavior. The paper concludes by utilizing the Wick's theorem, Theorem 2.1, to evaluate the determinant in equation 16. This leads to a new representation of the flagged skew Grothendieck polynomial as a sum over products of flagged Grothendieck polynomials, with coefficients determined by the variables z and wj. This representation is fundamental to the overall approach of the paper, as it allows for a more comprehensive understanding of the flagged skew Grothendieck polynomial in terms of its fermionic description. The research discusses the properties of flagged k-theoretic symmetric polynomials, focusing on their coefficients and their relation to the determinant of a matrix. It begins by presenting an equation for the coefficient of z lambda I minus iw micro j minus gin, z, w, which involves a complex line integral. The contour integral is shown to coincide with the residue of the differential form at t equals z, resulting in an expression for the coefficient. This coefficient is then compared with the determinant, 16, to conclude the theorem. The paper also remarks on the case where the parameters g1, g2, gr are all equal to 1, reducing the main theorem to a simpler form. This simpler form is further specialized to recover the fermionic presentation of the skew Grothendieck polynomial. The research draws from various fields, including geometry, combinatorics, and algebraic geometry, referencing several works in the field.